Okay, so we've got section 9.2, which is the binomial theorem. So binomial coefficient. So the binomial coefficients that appear in the expansion of a plus b to any nth power are the values of NCR for r 0, 1, 2, 3, all the way up to n. So classical notation, especially in context, is given by n over r, and choose r. So expand a plus b to the fifth using calculator to compute the binomial coefficients. So we would start with, so we have to do, whoops, not 10, 5, 0. Then we would do, so this would be a to the fifth plus 5, 1, a to the fourth, b, and we just keep going. 5, choose 2, oops, a cubed b squared, 5, 3, cube 1 to right a fraction, a squared b cubed, 5, 4, ab to the fourth, and lastly 5, 5, ab, oops, a is gone, b to the fifth. Because the coefficients will be descending. A's will count up. If you think about the FOIL, the first term will be all 5 a's multiplied together, a to the fifth. The last one will be that. So let's see here. 5. So this is 1. So 1a to the fifth plus 5a to the fourth b plus 10a cubed b squared plus 10a squared b cubed. This is going to be 5 again, and this is going to be 1 again. So that is the expansion if you actually worked out it. That's related to Pascal's triangle down here. So these rows are your exponent. So n0, n1, n2, n3, n4, and 5. The pattern is each number is the sum of the two diagonally above it. So, and the ones always fall down the edges. So this 2 is 1 plus 1 is 2. Here is 4, 1 plus 3 is 4, in the middle of 6. But these are actually what this stuff works out to be. I had to the fifth, so I look at this row, there's my coefficients, 1, 5, 10, 10, 5, 1. Okay, so here we have example 2. Show how 5 rows of Pascal triangle be used to trim row 6. So our row was it 1, 5, 10, 10, 5, 1. Okay, so the next row would be 1, 6, 15, 20, 15, 6, 1. So the expansion is going to be 1x to the sixth plus 6x to the fifth y plus 15x to the fourth y squared plus 20x cubed y cubed plus 15x squared y to the fourth plus 6x y to the fifth plus 1y to the sixth. So there you go. So recursion formula. So you could also think about it this way. Determine the coefficient of the term that contains x to the 10th in this expansion. So we're kind of working backwards. So let's see here. Term that contains x to the 10th in the expansion of x plus 2 to the 15th. So that's going to be this 15c10 x to the 10th, and then it's going to be 2 to the 5th. So I need to work out what that is. I'll work out what that is. So 15c10, oops, is 3003 x to the 10th, and 2 to the 5th is 32. So the coefficient is going to be 96096. And there you go. Okay, so here's your binomial theorem, which just lets you do just the expansion again. It gives you the rules. So expand this guy to the fourth, So here's our A, and this is our B. So we're doing to the fourth. So it's going to be 4, 0, our A term to the fourth, and our B term to the 0th, plus 4, 1. A term counts down, B term counts up, and we just keep on going. So 4, 2, 2x squared, negative y squared squared, plus 4, 3, 2x to the first, negative y squared cubed, and lastly 4, 4, 2x to the 0th, negative y squared to the fourth. So the 4, 0 and the 4, 4 are always 1. Now this is the fourth row, so it's actually, I can actually go back to Pascal's triangle if I want to. So it's going to be 1, 2x to the fourth is going to be, so 2 to the fourth is 2 times 16, x to the fourth, and anything at the 0th is gone. So plus 4, 1, oops, 4c1 is 4. 2x cubed is 8x cubed times negative y squared, negative y squared to the first, plus 4c2 is 6, so 6 times 4x squared times y to the fourth. Notice it's positive because I squared a negative thing, so that takes care of that one. Plus 4c3 is going to be 4 again, times 2x times negative y to the sixth. Multiply those, it stays negative. And lastly, plus 1, 2x to the 0th goes away, times y to the 8th. And we put this all together. So that is 16x to the fourth minus 32x cubed y squared plus 24 x squared y to the fourth minus 8x y to the sixth plus y to the 8th. So there you go. Now notice the y is counted by 2 because it's a y squared in here, where the x is only counted by 1 because it's a regular x. So there you go. And that, whoops, one more thing. Factorial identities. Prove that this is true for all integers. Let's see here. So this one is going to be n plus 1 factorial over, let's see here, so I'm choosing 2, and then the difference n plus 1 minus 2 factorial, minus n factorial over choose 2, and this will be n minus 2 factorial. So let's see here. What do we got? This is n plus 1 factorial over 2 factorial. This is n minus 1 factorial minus n factorial over 2 factorial n minus 2 factorial. So we need to expand so that we can cancel. So let's see here, n plus 1 factorial is n plus 1 times n, and then times n minus 1 factorial. I want to stop there because that's what I've got on the bottom to cancel. Same thing over here, n minus 1, and then n minus 2 factorial over 2 factorial, n minus 2 factorial. So those cancel, those cancel. So I'm left with n plus 1 times n over 2, because that's what 2 factorial is, minus n times n minus 1 over 2. So this is n squared plus n over 2 minus n squared minus n over 2. So that's n squared plus n minus n squared plus n all over 2. This negative sign goes to this and to that. So those cancel out. I have 2n over 2, which is just There you go. So what that's saying is that it's using this is you can always expand out either to the left or to the right if you want to. You just keep going down and stop your factorial where you need to once you've expanded it enough to cancel whatever's on the bottom. That is the end of the section.